Welcome back everyone, my name is Pedram and this is where we do advanced time series analysis, deep forecasting. Alright, Module 1, Demystifying Time Series and Modeling, Part 3. In Part 1 and 2 we talked about time series basics and forecasting strategies. Now let's talk about the exciting part, the modeling part. Okay, Part 3, Modeling. So in this part, we will start with the concept of white noise, what it is, why do we care about it, and then I will explain and compare classical time series modeling versus machine learning and deep learning at high level. Of course, the entire course is about modeling, and we will explore these time series models in details. So if you haven't watched the first two parts, please pause the video and finish those two parts first, as we are going to heavily rely on those concepts here. Now, without further ado, let's do Part 3. Okay, what is white noise and why do we care about it? So white noise refers to a random process with the following properties: zero mean, constant variance, and no autocorrelation. So here's an example of simulated data for white noise. We simulated for 1000 times steps, and as you can see, this is, the average is 0, so we have zero mean. We have a constant variance and there's no autocorrelation. If you plot the ACF, as you can see, for all the autocorrelation for the non-zero lags, it's almost 0 or not significant. So as you can see, everything is not significant. So we say that it's 0, right? So, and then if your white noise is coming from a normal distribution, we call it Gaussian white noise. It doesn't need to be necessarily normally distributed, but if it is coming from a normal distribution, we call it Gaussian white noise. Now, why do we care about white noise? What is the role of white noise in time series modeling? So here's a highlight. We are going to use it as a diagnostic tool. Basically, it's an indicator of a good fit. So what does it mean? It means that if you have a good model, then the residuals, what is residual? Whatever is not captured by the model, the leftover randomness. The residuals better look like white noise if you have a good model. If there's some pattern in the residual, then your model is not capturing everything. So let me show you a very simple example here. So imagine I have this time series, and I'm going to use a very simple linear model and with an upward trend. So imagine the blue line is the model, the red one is the actual data. And now if I want to plot the residuals is going to look like something like this. It's going to be something like this. And as you can see, this residual is nothing like the white noise, right? There's still some pattern in this residual, and that's telling me that that simple model, this linear trend, was not able to capture everything. How did I say that? Because when I look at the residual, it's not close to white noise. So we're going to use this as a diagnostic tool for our modeling section. We're going to build up some models and then to apply to the data, look at the residual, and we're going to judge, okay, based on that residual, is model doing a good job or not? So we're going to use it as yet another way of confirming that if the model is capturing everything in the data. Now let's do some very basic modeling together. So I'm going to work with some synthetic data, and they are very easy to follow and understand. So we want to talk about the concept of linear versus nonlinear data or model, right? So sometimes the data can be linear and we can model that data using a linear model, and the data can be nonlinear. We can model that data using either linear or nonlinear data, nonlinear model, right? So let's talk about these things. So imagine this is our synthetic data. Here we're working with 100 times steps, and these are the values, and clearly this is a linear trend. And again, this is synthetic data. I actually know the true process of generating this data, but we want to see if we can build a simple model together to back out that actual process, right? So, and as you can see, there is some upward simple linear trend. We can look at the ACF and PACF plots using them as diagnostic tools. And here the ACF, PACF suggests there is trend, but no seasonality. So we talked about it in the previous section. So there's a clear trend by looking at the ACF, but I don't see any seasonality because I don't see some scallop things like this, right? And from the PACF, it seems that lag 1 matters a lot. So if I'm thinking about a linear relationship in the data, maybe including one lag is good enough, right? And now the question is, can you think of a simple linear model? So I want you to pause the video and try to write down something. You don't need to be an expert. I assume that you have zero background. I just want you to use a pen and paper and try to write down a very simple model based on what you're seeing. And as a hint, I'm just plotting yt versus yt minus 1 for you. So this is actual data. This is data with one lag. And we know that one lag matters a ton. And as you can see, they're lining up almost perfectly. And here's some the first 5 rows of the data. Okay, pause the video and write down a simple model. All right, so hopefully you can get to something like this, right? You say, okay, yt minus 1 is 9.17, yt is 18. Then we have 18, 29, 29, 38, 38, 51, 51, 56. So it seems that our process is something like, the lag value plus some intercept plus the rest is noise, right? So this is exactly what we're doing. And actually, let me show you. If you do that, if you simply say, hey, the model is, let me actually write it down. So probably you did something like this. Yt is equal to some constant plus yt minus 1 plus some noise. Again, I assume that we know nothing about time series analysis and keep everything very simple. If we do that and if you plot the residuals, the residual of a linear model look like this. So this is a residual of your very simple model, right? So, and now you have to go back to the concept of white noise. Does this look like white noise to you, right? So is it stationary? Is the average 0? Is it variance constant, and etc., etc.? Obviously, you don't need to do it with eyes. There are some diagnostic tools, and you can run those things and see if the residual is stationary or not, right? And if that's the case, which is the case in our example, we have a good model, right? And now if I reveal the true model for you, this was the true model. Yt is equal to 10 plus some yt minus 1 plus some noise, right? And that noise actually was coming from a normal distribution, so this residual is going to be closer to the Gaussian normal. All right, so that was an example that the data was linear. So let me use my highlighter. So the data is linear, and we use a simple linear model for capturing the nuances in the data. All right, here's another example using simulated data. The data is obviously nonlinear. We added some noise, so this is your nonlinear data, and actually it's a combination of linear trends plus some perfect seasonality, right? So let's use our diagnostic tools and try to build a simple model from scratch together, right? The goal is to come up with a model that can capture these ups and downs, right? So I'm going to do the ACF and PACF plot. And based on those plots, I can say there's clearly a trend. By looking at the ACF, there's clearly a trend. There's clearly some scallop shape. So it means that the data is showing some seasonality. And when I look at the PACF, it says that controlling for lag 1, probably it's good enough. You don't need to be worried about previous lags, right? And this is all in linear fashion. Remember, ACF and PACF are showing the linear relationship between your random variable and its lag values, right? Not the nonlinear relationship. Keep that in mind. And yeah, so here the question is, can you think of a simple linear model that can represent this nonlinear time series data, right? And just for your reference, I plotted yt versus yt minus 1. And as you can see, it seems that they're lining up, but not perfectly, right? There's this gap that regardless of the value of yt, you get different values. Yt minus 1, you get different values for yt, right? So specifically look at these examples. For example, 60, 106. 106, 130, then 130, 127. So it seems that yes, as yt minus 1 increase, yt can increase or it can decrease. So there is this cyclicality. So what can we do? I want you to pause the video and put together some simple linear model. Remember, your data set is nonlinear. I want to see if we can use a linear model to capture that nonlinearity, right? And see if we can do it. All right, so maybe you say, okay, so let's keep things very simple and come up with the simplest linear model, right? You say yt is equal to, you can add a constant there, plus, and maybe based on this PACF, you want to say, let's add a lag value. I would say beta yt minus 1 plus some noise, right? And this is perfectly fine, but when you have a model like this, obviously you can throw the data at it and calculate the coefficients and plot the residuals, right? Let's go ahead and do that. So I'm going to take this model, This is a simple linear model, and look at the residuals. So let's see how the residuals are going to look like. All right, so these are the residuals of your linear model, right? So your linear model, and these are the residual of the linear model. Do you think these residuals look like white noise? Yeah, you might say, okay, the average is 0 to maybe, let me use another color. There you go. The average is 0, the variance is constant, but there's obviously some autocorrelation. So there is some clear pattern in this residual that the model is not capturing, right? So we're missing something, right? Then you might want to say, okay, so let's break down this. So obviously this is not a good model, simply because the residuals are showing clear pattern, right? Then we need to do something else. Then your next attempt would be, okay, can I break down this time series to its components, right? Because it's screaming at me, we need to have a trend component and some seasonality component, right? So what if I start engineering some features? I put together some features, and then hopefully when I add them linearly, it's going to capture the relationship, right? And this is exactly what we're going to do. We're going to say, you know what? Let's do this. So let me erase these ones. Let's see if I can use my eraser. There you go. Okay, so imagine these are the features that you're trying to engineer here, right? So, and my candidate features are, time step itself. So this is, let me use marker blue. So this is my first feature. All right. Well, actually, you're looking at the residual, but let me use my cursor. Okay, so this is feature number 1. I use the time itself as a feature, and then I'm going to use some sine and cosine components, right? Because these are going to capture some perfect seasonality, right? So now I have 3 components. The 3 components are going to be t, capturing the linear trend, and then sine and cosine. So my second model is going to be something like this. Yt is equal to, again, you can think of a constant plus, I have beta and then multiply t. This is my feature number 1. Let's say beta 1. Then I have beta 2 sine. Then I have beta 3, beta 3 cosine, right? And plus some noise. So this is my second candidate. And if I use that and calculate the coefficients and everything and plot the residuals, this is going to be the residual. So this is a residual, let me highlight it here. The residual of a linear, in parentheses, seasonal model, right? The model is still linear, but we use some feature engineering to capture that seasonality. And now when I look at the residuals, this look a lot better compared to the residual of a simple linear model, right? Without seasonality. So is it a stationary? Does it look like normal white noise? These questions, again, you don't need to use your eyes. You can use some statistical tools to answer these questions, but at least here visually we could say it's doing a lot better compared to the previous one. So maybe I don't see any strong pattern here in the residual. So probably the model is doing a good job. Now, if I show you the true model, then you can see how it did. So the true random process was something like this, 10t plus 100 sinus plus some noise, right? So actually your model was doing a great job. This is because this is reality and you were able to get as close as possible to the reality. All right, so the real examples out there are not this straightforward or this simple, but I hope that this past 2 examples, simulated data, show you how we start thinking about time series modeling from scratch, right? So you have to use some diagnostic tools like ACF, PACF. You have to do some EDA. This is your first step, and then look at the components of your time series. Look at the trend component, look at the seasonality components. And then when you want to put these things as together as a model, this is called the feature engineering part, right? So you're engineering some features to put them together, sorry, linearly or non-linearly, and hopefully to get as close as possible to the reality. But again, as I said, in real world, this is not as simple like this. We're going to look at the stock price in the next slide and see how far we can make progress. All right, now let's look into very complex nonlinear real-world data. And I just, for example, wanted to work with a Bitcoin price, right? So this is Bitcoin price as of 2024, and as you can see, this is obviously a very complex nonlinear time series. Now there are trends. We don't know if there's seasonality or not. The ACF and PACF plot suggest there's no seasonality, and then this is daily data, by the way. And there are some sudden changes in trends, right? Obviously there are cycles, but the trend is also changing frequently. So it's a very complex and nonlinear data set. And see how we can start approaching a data set like this. Can we use a simple linear model for modeling this? So let's start with asking the same question that we did for the previous examples. Can you think of a simple linear model? And as a hint, I show you the scatter plot between yt and yt minus 1. And it seems that they're lining up, but for different values of y, they are different, right? So it's not perfectly lining up, right? So again, this is yet another level of complexity of the data. Then what can we do? You can go ahead and use, look at the ACF and PACF plot, right? So for example, it seems that the autocorrelation is persistent, right? And as we go further down the road, we are using, let's say 20 lags here, but it's still, the correlation is plus 80%, right? So, and then on the other side, if we are using, I don't know, PACF, it seems that if you control for lag 1, it seems that everything is reflected in that. Actually, the autocorrelation, the PACF for lag 1 is close to 100%, it's close to 1. And this is a typical characteristic of a financial time series. It's pretty much close to random walk. We're going to talk about these details later on, but it's close to random walk. And it's basically hard to model when it comes to when it's something like that, right? But regardless, we're gonna say, you know what? Let's go ahead and use a simple linear model with 20 lags. Why not, right? And if I do that, so if I use that simple model with 20 lags, and if I plot the residuals, this is how the residual is going to look like, right? So again, this is a very simple model with 20 lags. Yt is equal to a constant plus beta 1 yt minus 1, beta 2 yt minus 2, and etc., all the way to beta, let's say 20 yt minus 20. If we do that and plot the residuals, this is how the residual is going to look like, right? And obviously, as you can see, there's something going on here, right? The residual is showing some heteroscedasticity, and the variance is changing, right? The variance is small here, the variance is getting larger. So obviously, this is not anything close to white noise, right? Again, maybe the average is constant and it's close to 0, but the variance is clearly changing. There is clear sign of autocorrelations maybe going on here. So we cannot say for sure that this model is capturing everything, right? And because there's a clear sign of nonlinearity in residuals, maybe we should have used a nonlinear and more complex model for this nonlinear data, right? Remember, our first example, the dataset was linear, we use a linear model. The second example, the dataset was nonlinear, we use a linear model again, and it was successful. The third example, the dataset is clearly nonlinear, and clearly a linear model is not working. Well, we can think of feature engineering more in depth, but maybe we should go beyond that, right? So maybe we can use some, I don't know, nonlinear and non-parametric models, including neural nets or some machine learning types of models, right? But the thing is that if you want to see, okay, what is a true model? The answer is I wish, right? So these financial time series, we wish we knew the model, and that's the reality for so many financial time series out there. But again, remember, many of the other business time series like demand forecasting, sales forecasting, they are more well behaved, right? So I'm showing you the extreme cases, a super simple data set and a super complex data set. And of course, yours might be something in between, right? Again, a demand forecasting is a typical well-known time series question that it's almost solved nowadays, right? So we know how to exactly handle those things. But just be aware, this is how the modeling aspect of time series data started back in the days. Starting from decomposing the time series into its components, creating some linear models, and then if it's not working, look at the residuals, make it nonlinear, and etc., etc. And this is exactly what we're going to do throughout the entire semester. All right, now that we are more familiar with time series modeling at a high level, let's put all these things together, the basics, modeling, and forecasting together, and talk about basic steps in a forecasting task. So step number one, problem definition, right? So this is the most important one. You have to sit and think hard. What is your time series task that you have? What kind of forecasting are we talking about? What is what horizon are you thinking about? Is it one step ahead or is it multiple horizon? If it is multiple horizon, are you doing those forecasts all at once, multi-output, or iteratively, multi-step, right? So these are very important questions. Then obviously the next step is to start collecting data, right? And when it comes to collecting data, time horizon is a big deal. Imagine you want to do some monthly forecast, right? And you're using monthly data. And the thing is that what if you could get access to weekly data or daily data? Or what if you could engineer some, I don't know, more high level data quarterly, annually, and things like that? So this is what you should think about, right? And start collecting data or generating those data sets, engineer those data for yourself, those variables. Then what is the structure of the data, right? What is the data type? Are you talking about, are you only wanting to use a structural data, basically simple rows and columns, or unstructured data as well, alternative data? Are you want to using, for example, images or voice? For example, for stock price, do you want to do conference calls, get sentiment out of them or not, right? Because depending on what kind of data set you want to deal with, you will be limited to what kind of models you can use. For example, our classical, traditional econometrics models cannot handle unstructured data. For them, you have to use, for example, deep learning models, right? So again, the data collection is the second step. Step number three, EDA. So this is one of the most important steps because you want to break down your time series into its components. What's going on inside that, right? You want to see if you can break it down to trend, seasonality, or if there's outlier. You talk about the stationarity of the data because all those things matter. If you remember from our previous video, why do we care about stationarity? Because if you're doing long horizon forecasts, of course, if the data set is stationary, your forecasts are going to be more stable, right? So things like that. And this is all done with EDA and using some diagnostic tools. For example, looking at ACF, PACF plus, looking at, I don't know, simple trend seasonality decomposition of your data set and things like that. All right, step number four, model selection and training. Then depending on specifically depending on the task that you have and the data structure, you will end up deciding, okay, what kind of models do I want to use? Is it going to be classical econometric models, or do I need more non-parametric or more complex models, including ML and deep learning models, right? And obviously, at the end of the day, as a practitioner, you can run a horse race between all these models and see which one performs better. But having said that, you should know in advance, that what kind of model is going to work better for your data set, right? So this is a skill that you should gain over time. And then finally, step number five, once you have a model, once you train it, you want to look at its performance, right? And performance-wise, let me actually write it down because it's very important. You have to always think about a benchmark. So what is your benchmark? Yes, these are your metrics. You're going to look at MSE, RMSE, mean absolute error, mean absolute percentage error, and et cetera, et cetera. But you should not look at those numbers in a vacuum. So you have to have a benchmark in hand. And that benchmark should be a fair benchmark, right? So for example, if your time series look like this, then obviously if I use simple average as a benchmark, this is not a good benchmark because a simplest model can easily output this benchmark. A better benchmark for this is going to be this green one. So maybe a drift model. A drift model is a better benchmark, right? So things like that. First of all, think of a benchmark, and secondly, think of a fair benchmark. This is important. And then compare the performance of the model that you put together with that simple benchmark using these metrics, for example, RMSE or mean absolute error, mean absolute percentage error, etc. Okay, we talked about the basic steps in a time series forecasting task. Now let's look at a very simple example and talk about modeling in general, not necessarily only forecasting, and see when it comes to modeling, where should we start and then how we can make that simple model into a forecasting model and what are the differences, right? So I'm going to stick to a very simple example, which is quantifying airline passengers, right? At the end of the day, we're going to see, okay, so for example, we have data for different countries, for different random variables, and you want to see what is the number of airline passengers for each country at each point in time, right? Depending on the data availability, we can come up with different kind of modeling, right? So if you have a cross-sectional data, obviously you have to build a cross-sectional model. If you have a time series data, you can think of a time series data. If you have panel data, you can do a panel data, right? A panel model, right? And then again, depending on the availability of the variables, you can think of a univariate time series model, univariate modeling versus multivariate modeling, right? And so let's start from a very simple data set. Imagine, just for the sake of argument, I'm telling you that this is the data set, right? So we have something like this. In this data set, we have only, let's say we have multiple countries, right? I don't know, you have USA, you have Germany, you have France, you have Italy, and etc., right? And then for each of those countries, you have passenger data. No, passenger, let me just say passenger information. Let's see. Number of passengers. You have the country GDP. And I don't know, you have their unemployment, some macro variables, right? Unemployment and et cetera, right? If I tell you that, hey, this is a data set that you have, and you're supposed to put together a model, the only thing you can do is a cross-sectional data, right? Because you have number of passengers, GDPs, unemployments, and etc. And you can use it, for example, you can say, hey, this is my target variable, these are explanatory variable. You can put together an explanatory model in a cross-sectional manner, right? So this is one possibility. And so for example, you can start with a simple model like this. Airline passengers is equal to a constant plus beta 1 GDP, beta 2 unemployment, beta 3 saving, and everything else is going to be basically squeezed in some noise, right? So if that's the case, then you would say, hey, this is my explanatory model, right? Then you can answer this question. Can you interpret this model? You have taken, I don't know, econometrics courses before, some machine learning basics before. You have seen me talking about these things before, but just one last time I want to do that. And I want to emphasize the difference between this kind of modeling and time series forecasting modeling, right? So can you interpret this model? The answer is absolutely yes. We put them together in a linear fashion. This is the simplest model we can have. Then if you throw data at it, it can talk about significancy of these coefficients and it can interpret them, right? So for example, I don't know, if some countries GDP is larger, probably the number of air passengers might be larger too, right? This is just a hypothesis. You can test those things and you can answer interesting questions like that, right? Then the next one is, can you make prediction using your model, right? Obviously you can do predictions. So the reason that I'm highlighting these terms is that I want you to distinguish between the term predictions versus forecasting. So prediction is more general, right? So obviously I can do in-sample predictions here. I can say, or I can make some predictions for new countries that I don't have information. So for example, I have another country here, and then I have its GDP, the number of, not number of passengers. I have its GDP, unemployment. I want to predict number of passengers, right? So this is doable. Yes. Can you make prediction using this model? The answer is yes. Then the third question is that, can you make forecasts into the futures? What are the challenges? And then you might say, okay, if this is the data set, so far there's no sign of time in this data set. Maybe this is one cross section in 2024, right? This is the data we have, but there is no time component here, so I cannot forecast into the future. So the first thing you need to have is the values of these variables, number of passengers, GDPs, unemployment, savings, and etc. over time, right? So right away, you need to have access to a panel data. For example, it's going to be, let me use another color. So for example, for US, you're going to say, I don't know, quarter 1, 2023, quarter 2, 2023, quarter 3, 2020, and etc., etc. So you have to have access to all those information for all the variables as well, right? For each country, you need to have those ones. Now, this is a panel data. Obviously, you can create a model and do some panel regression and then interpret things at the same time. So far so good. We're adding the time component, but can you forecast into the future? If you want to do that, so it's going to become a little more challenging. So here, let's talk about the challenges. If I want to forecast, for example, a number of passengers in USA in 2025, in 2026, quarter 1, quarter 2, quarter 3, whatever. Then if I model like this, then I need to have access to the GDP for USA in next couple of years, unemployment for USA next couple of years, saving next year for the next couple of years, right? So this is going to make it a bit more challenging, right? This is a multivariate time series forecasting. And then who would say maybe if you want to do that, maybe you would be better off just do a univariate time, use the data for US and then look at the passenger data and make a forecasting model into the future. So hopefully you're realizing what I'm trying to say here is that this is general modeling. Based on the availability of the data, you will figure out what kind of models you can put together, right? And sometimes we do it from the other way around. We say, I want to do a forecasting task. So you have to go out and start collecting data. So with this background, now let's look into the basically some terminologies. For example, predictive model versus forecasting, or I don't know, we're going to talk about explanatory models or static models versus dynamic models. So let's talk about those things. Okay, focusing on the forecasting task, and I'm going to use only one country to make things simpler. Let's write down a model. First of all, we are going to see, hey, we have this time components now because this is a forecasting task, and I'm only looking into USA, right? So let's say to just one country. So let's say this is the data USA, and then we have these things, you know, number of passengers, GDP, unemployment, and saving. And we have, or no, this is time, right? Q1 2020, Q2 2020, and etc. Q4 2024. Okay, so let's say this is quarterly data. If that's the case, we can put together a model like this. Airline passengers at time t is equal to some constant plus GDP at time t, unemployment at time t, saving at time t, and unobserved variables at time t, everything else, right? So what is this model? This is an explanatory. So here are the terminology that I want you to become familiar with. So this is our explanatory model. As the name suggests, we put together this model to explaining the status quo, right? So this model is contemporaneous. We call it a static model. And but for a forecasting task, we need to make it a dynamic forecasting model, right? How can we do that? I want you to pause the video and think about it. How can I change this model, into a forecasting one? All right, so we can do something like this. We can say airline passenger at t+1 and using the same equation. So what does it mean? It means that use this, for example, row of data and try to make a forecast. Use this value to let's say this is Q1 2020. Use this row of information to make a forecast for Q2 2020, right? So by adding this t+1 component, we are making this model to become a forecasting model. It's a dynamic model now. It's not contemporaneous anymore, right? Again, the data is the same. The data is exactly the same. Now I'm changing my target variable from yt to yt+1. This seems very, I don't know, simplistic, but it's going to do the job, right? Simply, we're going to regress yt+1 on everything from the previous time step, right? So this is going to be our forecasting model, right? So now we're going to say, okay, let's make an assumption. Let's assume that everything is reflected in passengers' numbers, right? I don't care about explainability of this model. I don't care what is the impact of US GDP over quarter on the airline passenger or unemployment rate or saving. Whatever it is, I'm going to assume it's reflected in airline passenger. If that's the case, I want to rewrite the model like this. So why not passenger t+1 is a function of passenger at time t, passenger at time t-1, passenger at time t-2, and etc., etc. So it's only a function of one random variable, which is passenger, but I'm looking at different lag values, right? So let's say this is our forecasting model that we have in mind. Now let's talk about this model. So what is the goal? What is the goal of this model that we put together? We call it the dynamic forecasting time series model. And we know that it's a function of passenger at time t and t-1 and etc. And the goal is to identify existing patterns in data to project future patterns, right? So I tried to be color coded here. So the existing pattern is whatever you have from the trained data set. Imagine this is your train set, right? And you want to come up with a solution for this functional form. What is this f, right? And that's basically the thing that's revealing the pattern in the data. How can I connect the relationship, the variables, the lag values, let's say, together to generate something like this? That functional form, if it is super simple and linear or any other fashion, parametric one, you can think of it as a classical models. If it needs to be more complex and nonlinear and non-parametric, you can think of machine learning and deep learning models, right? So that F, this is the pattern. This is the pattern in data that you're interested. We're going to use trained data set to find that pattern and then apply the same pattern into the future time steps, right? So this is what we're going to do, right? So we want to project the future patterns. So that's the task. And I think the highlight of this slide is, at the end of the day, what is this F? How do we model this F, this functional form? Do we need to make some assumptions? Do we need to restrict it? And what do we do? Basically, answering these questions is going to tell you either you're using classical model, machine learning model, or deep learning model. What is that pattern recognition thing? And as I said earlier, this F is going to tell us what kind of model are we dealing with. Is it machine learning, deep learning, or econometric? So how do we identify these functional form or this F, right? We can start with a very simple one. So for example, say, hey, the passenger t plus 1 is equal to a simple linear relationship, some constants plus some constant multiply passenger t, constant passenger t minus 1, and etc., etc. So if you're imposing this functional form, which is linear, by the way, here, on your f of f of data, right? Then this is going to be your classical models. If you want to make it more complex, then or you want to think of non-parametric approach, you have to go beyond that, right? So we are going to see, for example, in machine learning, we're going to do random forest. So random forest, we're not imposing anything on this F, right? We're defining some architecture, some structure, some algorithm, but we're not imposing anything on that F. Neural network, the same idea, right? So basically that's why and how we need to go beyond classical models. If you want to make this F of data more complex, more flexible, let's say, to capture more nuances in the data. I think now we're ready to talk about predictive modeling versus forecasting. So this is a very simple table. I just want to compare them at a very high level and make sure that you don't confuse forecasting versus predictive modeling. Forecasting actually is a subset of predictive modeling. It's nothing new. It's a subset of that. And here actually, let's go over the definitions and the focus, and hopefully it makes more sense. So in predictive modeling, the definition is something like this. You're creating models to analyze data and predict an outcome, right? So, and depending on what kind of data you have, you can do cross-sectional modeling, you can do multivariate, you can do panel, and etc., etc. In forecasting, however, you're making informed predictions about the future. So the key term is future. So it's all about future events, right? Based on the past data. The focus on predictive modeling is any point in time. So you can use predictive modeling to explain past, present, and future, right? If it is cross-sectional data, it's at one point in time. However, for forecasting, again, we are focusing on future outcomes. And in terms of variables, predictive modeling, we typically do multivariate because you want to explain things, in their status code. Typically, there are static models. But for forecasting, typically there are dynamic models, and we do univariate modeling, right? Because again, if you want to forecast into the future, especially for the longer term horizons, if you do multivariate, it's going to be kind of complicated, right? Because you need to make forecasts for all those variables. Let's say you have 100 features, you have to forecast all those 100 features into, I don't know, 10 steps into the future. So that itself is a different problem, right? So if anything, it's going to add more noise to your data and make the forecast in the long run less stable. So for time series forecasting, we can use either econometrics, machine learning, or deep learning. So let's talk about these three categories at a high level in the next slides and wrap up this section. All right, starting with econometrics. These are our classical time series models. These are purely, let me use my marker. These are purely decomposition-based models, right? You're creating these models from scratch and putting them together. So it focuses on modeling through decomposition and autocorrelation, right? So for example, if you have a time series, you can decompose it into trend, seasonality, and let's say the error term. That's your ETS model, right? This is the ETS family of models, which is very powerful, especially if time series has pronounced trend and seasonality, ETS family is gonna perform. And sometimes we're going to look into decomposition based on autocorrelations, right? So this is actually what the ARIMA family is doing. ARIMA stands for autoregressive integrated moving averages. This AR component is going to focus on autoregressive part. The MA is modeling the error term using moving averages, and I is taking care of if the data set is stationary or not, right? By doing multiple differencing, it's going to make sure that the data set is stationary and your long-term horizon forecasts are more stable, right? And then if you want to add some, so in this ARIMA family, if you want to add some features, use it as a multivariable, you can do that. It's called ARIMA X. So this is your set of features. And if you want to add seasonality, we have SARIMA X, right? And this is again, this is a functional form for your ARIMA model, right? This is parametric structure. Parametric structure simply means that we have defined mathematical forms. Remember that f of data that you were trying to estimate, you were trying to figure out. This is the pattern you're trying to recognize. That thing, if we impose some functional form on that, if we define some mathematical forms on that, it will be our parametric structure, right? So the econometrics-based models are mainly parametric structure. So for example, this is just one example, how we are putting together those components, right? So for example, these are the lag terms, and these are how we are adding the error terms to the data. And in terms of statistical tools, the econometric models is going to give us the confidence intervals, and nowadays we talk about conformal intervals and things like that. They are perfect for hypothesis testing to give you some insights, right? These models are very interpretable because again, look at your f of data. This is some simple model put together. You can exactly see where, for example, the changes are coming from. They're interpretable, they're explainable, and it's perfectly used for hypothesis tests. And again, this is at a very high level. Later on, we're going to talk about the details of ETS and ARIMA in general, and maybe we cover some of the other extensions like, I don't know, the BATS, TBATS. So these are some different models. So basically, I would put BATS and TBATS in this part, which we're looking at decomposition. So BATS simply stands for basically Box-Cox transformation and ARMA errors, trend seasonality, right? You're decomposing the time series into its components, and then if your time series, for example, it's showing some, I don't know, needs some transformation, we're going to use Box-Cox transformation first and then apply those decomposition, right? And then TBAT, it basically is using trigonometrics, the components like sine, cosine, and tangent, right? So again, these are at the high level. Remember, the econometrics models, the classical models, are decomposition based. Let's break down a time series into its components. That's why the EDA part is super crucial here, because you're building these models from scratch and putting the components together in a linear or nonlinear fashion. And the same story for ARIMA. Here we are focusing on the stationarity of the data and the AR components and autoregressive components. All right, so here is our airline passenger data, and as you know already, this data set is super well behaved. You can easily decompose it into its components, trend, and seasonality. For a data set like this, ETS model, which decomposes the time series into error, trend, and seasonality, is going to shine, right? So if you have a simple, well-behaved data set, I would say you can stick to your simple classical econometric models, including ETS, and you don't need to go beyond that. You don't need to do complex machine learning or deep learning, because this model, here I'm using PyCaret, and you'll see that you can see the prediction intervals as well as the point forecast for your forecasting horizon, which is in this case 24 months into the future, right? And now let's look at the limitations of econometrics, why we should go beyond that. If we have a well-behaved data set, then we would say, I don't know, ETS, ARIMA, all the other classical models can outperform, can shine compared to the benchmark. But if the data set is not well behaved, and in our course we're going to look into, I don't know, the most complex time series, which is, I don't know, stock price, we will see that it's not simple. You know, the classical models cannot handle this kind of a strong, complex nonlinear relationship. Because if you want to start decomposing this time series, which is Apple's stock price, into its components, you will see that it's basically everything is in trend, and the trend part is going up and down, and it's very complex. And we cannot simply use, maybe we cannot simply use econometrics model. We should go beyond that. So in this plot, you are basically looking at Apple's stock price. This is the adjusted close. And I'm showing some benchmarks for you, right? So for example, this purple one is the grand mean forecaster. This is your simple average. So going over these entire time steps, take a simple average, and that's the number. So you're using multi-step forecasting to the future. Look at that. This is your forecasting horizon. And we're using multi-step forecasting to the future. And this is, by the way, again, created by PyCaret. We're going to cover the details later on. And your naive forecaster is the red one. This is the last observation that we use. In the train set, we use it for all the forecasting horizon in the test set. So that's the red one. And then let's say, which one is a better benchmark? Obviously the red one. And then you want to outbid that one, right? Here, I'm showing you the ETS in green and ARIMA in orange. Look at that. ETS is predicting something upward sloping into the future, and ARIMA is predicting something downward sloping into the future, right? And as you remember from part 2, I highlighted that when we were talking about forecasting horizons. If you have multi-step forecasting horizon or multi-horizon, then it's going to be super sensitive to the number of horizon you're using, right? So for example, here we are using this horizon. If I narrowed it down to, I don't know, this horizon, probably maybe ARIMA and ETS were both telling you that it should be go downward, right? But as you can see, when I change the time horizon, the ranking of the models is super sensitive to that. So we talked about it already in part 2, but here's just another example. So when we have something like this, you know, when you're comparing different classical models, and if you change the forecasting horizon and the ranking of the models change dramatically, this is a clear sign that this dataset is not well behaved. It has a strong nonlinearity in it, and we need to transition to machine learning. So that's why we actually in this course we're going to cover all of them. We will talk about machine learning, deep learning models that they are. We know that these models are inherently designed to capture complex and nonlinear patterns. And what is the trade-off? The trade-off is that they're not interpretable. They're not as interpretable as our classical models. But in general, you have to keep all these models in mind when you're doing time series forecasting. And as I said earlier, as a practitioner, you can, at the end of the day, you can run these models side by side and see which one performs better based on the context, based on the nature of your time series. The second set of models that we're going to explore in the course are the machine learning ones, right? So probably you're familiar with some machine learning concepts like supervised, unsupervised, semi-supervised, and self-supervised. Here we will be focusing on supervised regression tasks. So this is when I talk about machine learning time series forecasting, this is where we are, right? We want to focus on supervised regression. So that means that your first task, if you're doing machine learning time series forecasting, is data transformation. So if you haven't seen this, if this is the first time you're seeing machine learning time series forecasting, this should be probably new to you. So let's talk about that one. So imagine I have this airline passenger data, right? And this is my data set. Let's use the right color. So this is my data set, whatever it is, right? And you might think about it, okay, this data set has only one variable, right? And that one variable, let's say it's passenger. And let me show you the YT. And it's something like this. I don't know, 100, 105, 110, etc. So there's only one variable. So what do you mean that we have to transform it into supervised regression model, right? There's only one variable. How can we do that? So that's the thing that we're going to cover in next slide. So your first task is to pre-process the time series into a supervised learning format. So basically, by using only this one variable, you have to create some extra features. Those features can be simply the lag variables, or it can be simply some external variables, right? The moving averages of the lags and etc., etc. But whatever it is, we have to create that data set. We have to create that supervised data set first. And so again, this is your target and these are your features. And then apply any kind of machine learning model to that, right? It can go from a simple linear machine learning model to random forest, XGBoost, you name it. So because for some of the machine learning models, we are not imposing any functional form on that f, then they're more flexible, right? They can capture more complex and nonlinear relationship without explicit mathematical models for the underlying process, right? And with the machine learning models, they are not as interpretable as the econometric models, but they're still, they can give you some interpretability, especially when you're using some boosting methods or random forest family. We can talk about feature importance, right? You can at least rank those features for yourself, right? This is going to offer insights into which of those features are most important in terms of your predictions, right? So what are the challenges? The challenges are, because these models are more complex and some of them are non-parametric, they can easily overfit, right? So we have to deal with that. And in order to avoid that, we can use some cross-validation or some bootstrapping. But we know that if you're doing cross-validation or bootstrapping, if you're sampling, let's, for example, bootstrapping is repeated sampling, right? Or cross-validation is just shuffling the data and then just do sampling, right? But the problem with time series is that time series data, of course, is not IID. We know that that's the whole point of time series. The correlation, the autocorrelation between lags, definitely is not going to be zero. And because of that, you cannot simply shuffle the data, right? So you have to use some special forms of cross-validation, or we call it time series cross-validation. You know, for example, moving forward or expanding windows, embargo, purging. These are different ways of correct time series cross-validation. And also the same story for bootstrapping. You cannot simply use simple bootstrapping with, I don't know, sampling with shuffling the data, because this is time series. So we have to use a special form of bootstrapping that we talk all about these details later on. So be aware when you use machine learning, there are some challenges attached to that. That as a practitioner, if you blindly use scikit-learn random forest and apply it to a time series, probably you're doing it wrong. So you have to be careful of those things. Okay, now let's talk about that machine learning data transformation step, which is the most important part of doing time series machine learning, right? So imagine you have a univariate time series, and this univariate is only y, and you have 10 time steps, and this is your simple time series, right? It's a trend going up, down, and go up again, and etc., right? And this is a synthetic data, synthetic upward trend with some variations. And this is the data set that you have, time series raw data. Your raw data is something like this, y1, y2, y3, all the way to y10. So in this example, your y1 is 7.4, and your y10 is, what is it, 16 point something, maybe 17, right? So you have simply you have 10 numbers. How can you apply a machine learning model to that? So you have to transform them into a supervised data, right? And this is how we're going to do that. So your target variable is going to be your y, and your features are going to be different number of lags that you're using. Let's say in this example, I use 4 lags. So I'm going to use yt minus 1, yt minus 2, yt minus 3, and yt minus 4. So let me actually highlight some stuff so you're going to understand it better. So imagine this is our first row of data. I'm using the past 4 observations, 1, 2, 3, 4, y1 through y4 as features. These are the x's, x1, x2. So you can think of it as x1, feature number 1, x2, x3, x4. Okay. And then with that, I'm going to make a prediction for next time step, right? Which is y5. That's it, right? And then next, so this is one observation. So this is your one observation. Then your second observation is this, right? So the second observation in your data set is something like this. And then this is your last observation. For example, okay, 1, 2, 3, 4, 5, 6. This is the sixth observation in your data set, right? So we're using y6, y7, 8, 9, and then this is your target variable, y10. Okay, so hopefully it makes sense. We had a simple data set like this, raw time series data, and we have to transform it into a supervised time series data. Now I can apply, again, any kind of machine learning to this y and x. You have a bunch of features, you apply your machine learning models to those features to make a prediction for your y, right? So, and then remember, this is univariate time series forecasting. And it's univariate simply because you're using just one variable here. Do not confuse that you're using 4 features. Yes, these 4 features are basically coming out of the same variable. For example, airline passengers. You can do multivariate time series forecasting for machine learning. If you want to do multivariate, then you have to add more features, right? And what are those features? So for example, I don't know, we have x5 and x6 here. Let's say x5 is basically you're doing some moving averages, right? x6 you're adding some holidays, x7, etc., right? So you can think of any features you want and add it to your machine learning model. But be aware, those features that you're adding better be forecastable into the future easily. For example, holidays are easily forecastable into futures, right? And things like that. If there are random variables themselves, then we get to the same problem that we had with the econometrics, because multivariate time series forecasting is generally more challenging compared to univariate. Okay, in the previous slide, we covered machine learning data transformation when we had single output, right? But here, what if we want to have multiple outputs? So what does that mean? So let's go back to the examples again. Let's use red. And imagine this is, now our target variable is going to be simply different. So let's going back to the same univariate time series, right? Y, and then I have the same 10 observations. Y1 is equal to 7.4, Y10 is equal to 17, and etc., right? So the same time series raw data, and I want to transform it into the machine learning time series with multiple outputs, right? So this means that your target variable is not only one variable now, it's 3, right? So it's, and that 3 depending on what is your forecasting horizon. If my forecasting horizon is h is equal to 3, basically I have 3 targets to estimate, right? yt, yt plus 1, yt plus 2, right? So my first observation is like this. Use the past 4 days of information, so y1 through y4, to make a prediction for the next 3 days, if this is daily data, right, at the same time. So it can be either at the same time or multi-step or iteratively, but here we're focusing on at the same time, multi-output, right? So let's show it. So imagine, again, this is your first observation, the yellow ones. We're using them to make the forecast for the next 3 days at the same time. So the purple ones, we're going to make these predictions at the same time. All right, so now let me talk about one last thing before we move on, because not all the models are able to create something like this. For example, your econometric models, the ETS, ARIMA, are not designed to generate this multi-output. However, your machine learning models are, and the deep learning models, for sure, they're capable of that. When it comes to deep learning, it's easy, right? We know that, for example, we're going to talk about neural networks later on, but if your output layer has 3 nodes, it can create 3 separate forecasts for each of those nodes and then call it multiple output. But for machine learning, it's a little more tricky because remember, guys, linear regression is a machine learning model, right? How can it generate 3 outputs? So that might be a little confusing. So let me talk about that, because not all the machine learning models are by default giving you multiple outputs. For example, linear regression does not give you multiple outputs by default. However, if you want, you can create that. So what do I mean by that? So imagine I have something like this. So I'm going to say I have a linear model, right? And that linear model is something like this. Yt, I'm regressing it on yt minus 1, yt minus 2, yt minus 3, and yt minus 4 here. So this is one model. I have one output for this model, and the output is y hat t, right? Can I do this? Can I regress yt plus 1 on the exact same thing? The answer is yes. And remember, this is yt plus 1 on everything else. This is going to give you another output, y hat t plus 1. What about I create another, I run, again, the model is the same model. This is simple linear regression, but I'm just changing the target variable from yt to yt plus 1 to yt plus 2. So this is yt plus 2. Now let's regress yt plus 2 on the same data, yt minus 1, yt minus 2, and etc. Right? And obviously it's going to give you y hat t plus 2. As you can see, I can use a simple linear regression, let's call it simplest machine learning model, to create 3 outputs at the same time if I run the same model using 3 different target variables, right? So yes, it's doable, but it's not using all the information together. It's not using yt and yt plus 1 and yt plus 2 together, right? So this is so that's why we're going to say if you're doing a linear regression for machine learning, we will not do multiple output. However, if you're doing random forest, because random forest can generate this yt and yt plus 1 and yt plus 2 at the terminal nodes at the same time, so we can do that. So that's why when I say not all the machine learning models are able to generate multi-output, this is what we mean, right? Practically they can, but typically we don't do it that way. For linear regression, we don't do it. For random forest, we do it because the model is capable to do that. And for all the deep learning models, they can generate multi-output because simply you're going to change the number of neurons in the last layer from 1 to h, whatever forecasting horizon you have. Hopefully that was clear. Okay, so here are the list of machine learning models that works in practice for time series. So as you can see, I don't list, for example, KNN regression here for time series because again, in practice, it doesn't work as well as other machine learning models. We always are gonna use linear regression as a benchmark. Definitely, we're gonna include that in our arsenal, and then in this course, I will focus on boosting techniques, bagging and boosting based on this simple decision tree models. So we are going to cover random forest, XGBoost, light GBM, cat boost, and etc. So these are the ones that has historically shown a better performance when it comes to time series forecasting tasks. For example, let's apply our random forest to simple airline passenger data, right? And now hopefully this terminology makes more sense. When I say random forest with 12 lags, so these are my x's that I'm using, right? These are the features, right? So for example, this is going to be my yt plus 1, that's the target, and the x is going to be yt minus 1 all the way to yt minus 12. So I'm using 12 lags as features to make a prediction for my yt. So if I do it this way, this is one step ahead forecast. So let's do orange. This is my one step ahead forecast, right? And the one step ahead forecast for this data set is something like this. I'm trying to highlight it, okay? And yeah, there you go. And then obviously we can go ahead and create multi-step forecast and multi-output forecast. So multi-step is going to be the green one. And if you compare it to the actual, which are the blue ones here, multi-step is doing okay, but it's not capturing this increase in trends, right? So we're going to talk about all these details, what's going on here. So I have a Python notebook for you, which is going to talk about all these details, why exactly random forest with 12 lags is not capturing that upward trend, right? And we need to do something to that. So we're going to talk about all those things. And then multi-output is our red one. And this is if in your decision tree based models, you are creating multiple outputs at the same time. And again, this one is capturing the upward trend, but it's kind of off, it's kind of shifted a couple of time steps, which is not necessarily good, right? But again, this is a very basic random forest with 12 lags. We're going to do a lot better than this by doing some twists and tricks. But look at that, for this, we already talked about it. For this simple data set, which is well behaved, we knew that ETS and ARIMA are gonna shine, right? But regardless, we can go ahead and apply random forest and see how it performs. All right, and finally, the last set of models that we're going to cover in the course are the deep learning ones, right? So the goal of deep learning is to build a model that can automatically learn complex patterns, can learn nonlinear patterns in the data. And the key term is that automatically, right? You want to do this feature engineering that we did for for example, classical models, all automatically, right? So just like machine learning, deep learning models requires data transformation as well. So imagine we are working with a univariate time series forecasting, and we have a neural network here, and the first layer, which is our input layer, is going to take some inputs. What are the inputs here? Let's say we have, yt minus 1, yt minus 2, yt minus 3. So let's say we have 3 lags, right? And then we are going to, the output layer, if it is let's say single output forecast, you can say, okay, go ahead and predict yt. If we have multiple output, we can simply create more nodes and then just say, I don't know, this is yt plus 1 at the same time, right? So that's basically how easy a neural network can create multiple outputs by adding more nodes at the output layer. So a neural network, the beauty of neural network is that you just pass the input layer, which are the, let's say, features, right? And these features, by the way, again, if it is univariate time series forecasting, it's this. If it is multivariate, it can be anything. It can be a combination of those things. It can be, or it can be any kind of other random variables. It's going to take these inputs, and by adding a bunch of layers in between, we call them hidden layers. We're going to talk about the details later on, but basically it's going to explore all the possible relationship in those inputs, right? So it's going to explore all the nonlinear relationship, all the complex, let's say, interactions between those lag values together as well. And how does it do it? So the thing is that it's going to pass through this network once and create an output. Let's stick to a one output example. Let's say this is yt. Okay, so this is your prediction. And then, of course, you're going to compare this prediction to an actual value, right? So obviously, when you do y minus y hat, you're going to get your residuals. Then you're going to go back through network. This is called backpropagation, to update the weights of these connections by minimizing the summation of these residuals, right? A metric of these residuals, that's your loss function. Typically for regression, we can do mean squared error, right? So the summation of the mean squared errors. And yeah, so it's gonna update those weights and figure out the best relationship between these features that's representing the data, right? So this whole thing is automated. It's automatically done in deep learning. In Econometrics, we did feature engineering, right? We said, hey, this is trend component, this is seasonality components, added together. In machine learning, it was semi-automatic, right? Some of the models, like linear regression, we had to do it manually. Some of the other models, it was semi-automatic. But in deep learning, it's completely automated, right? This idea of capturing the patterns, capturing the complexity in the data automatically, this feature engineering is done automatically using deep learning. Okay, now let's look at our simple airline passenger data and apply a simple deep neural network with 12 lags in it. And now hopefully again it makes more sense when I say 12 lags. Simply means that we're doing this. This is your target variable and this is your features, yt minus 1, yt minus 2, right? So target x. If you do something like that, and remember, look at this is your input level, 2 features, and I'm adding, by the way, I'm rotating this network to just fit in here. I'm adding 2 hidden layers, one with 24 neurons, and then the other one with 8 neurons, and this is simply our one step ahead forecast, so that's why we only have one output node, right? If you want to do multi-outputs, you're going to add multiple of them here. Okay, so for now, let's look into this one. So the one step ahead forecast is going to look like this. So the orange one. So this is our one step ahead forecast. It's doing an okay job, right? And we're only using 2 lags. So this is really important. It seems that by only using 2 lags, the model is doing okay in terms of one step ahead forecast. But when it comes to multi-step ahead forecast or multi-output output forecast, the model is having harder time, right? So let's look at the multi-step ahead. So the multi-step ahead is the green one. Oops, sorry, I used green as the green one, and then the multi-output is going to be the red one. Okay. So it seems that both for multi-step ahead and multi-output ahead, it's capturing an upward trend, but barely speaking to seasonality or things like that. So obviously we don't have a good model when it comes to multi-step and multi-output. And the reason is that, remember guys, this neural network is using nothing. It's just using two lag terms, right? So one way to fix it is that let's use more lag terms, because this is a monthly data. Let's use at least 12 lags to capture the seasonality, right? And then on top of that, if you want to capture longer term dependencies, you have to completely change the architecture, right? So in the next slide, I'm going to show you when we use, for example, 12 lags. So here we are using 12 lags. So this means that our feature space has 12 dimensions, right? So 12 lags. And then the same hidden layers, 24 and 8. And then this is again one step versus if you want to do multiple step or multi-output, right? So here, if you look at the performance, all for one step, multi-step, and multi-output, you're doing an okay job, right? So this is of course a lot better than when you compare two lags. And the reason is that it seems that for this very simple, very well-behaved data set, including 12 lag was enough, simply because it's capturing a short-term dependency in the data. The data is showing monthly seasonality, so maybe having 1 year of data to forecast the next observation, it's good enough, right? And but what if your data set is showing longer-term dependencies? Then only including 12 lag is not enough. And the answer is not simply by adding more lag. So that's not the answer to everything, right? So maybe we should change the architecture. That's why we need to go beyond deep neural networks architecture. We have to do, for example, some sequential modeling, for example, the LSTM, RNNs, and et cetera, et cetera. And those are the topics that we're going to cover in detail later on. So these are the neural network architectures that we're going to use for time series forecasting. We will definitely explore standard neural network, and then we will talk about the limitations, and we say why we should go beyond that, why we should use some sequential modeling. We talk about convolutional neural networks. We know that this is designed for image processing, but we can also apply it to time series data, and we're going to look into that. And then finally, we're going to do recurrent neural networks, right? Because these are structurally designed to capture temporal dependencies and long-range sequences in time series data. In this course, we're not going to cover transformers, simply because we still do not have enough evidence to suggest that transformers offer significant benefit considering their implementation costs, right? Especially in practice. Remember, imagine you're using time series forecasting to create a trading strategy, right? These forecasts need to be updated in large scales and frequently. And the more complex models, for example, in transformer architecture, it's going to be computationally heavy and more restricted, right? So, and again, the benefit is not, at least as of now, it's not as clear as it's worth to just pay the cost for that. So that's for that reason, I'm not going to cover transformers in this course. All right, let's wrap it up by going over modeling comparison. So here is in one slide, in one table, I'm going to compare econometrics versus machine learning versus deep learning modeling when it comes to time series forecasting, right? So let's look into different aspects and see how each model is behaving differently. So starting with feature engineering. So econometric-based models, these are our classical time series models, right? The econometrics models requires explicit modeling of components. Remember, these are decomposition-based models, right? So you have to feature engineer those things from scratch. You have to create those features and put it together in a linear or nonlinear fashion. So this is the econometric approach when it comes to feature engineering. Machine learning, it depends. It depends on what kind of machine learning model you're using. That can be completely manual or kind of sort of automated. For example, if you're doing a linear regression model, then it's going to be, you have to create those features, right? And deep learning, it's going to be mostly automated, right? So actually, the whole point of doing deep learning is to just make sure that feature engineering part is kind of automated. Then, in terms of model complexity, obviously the econometric models are the least complex, and then machine learning is moderate, and then deep learning is mostly complex, right? Because they are suited for complex and high-dimensional data in general. Interpretability, because econometrics ones are less complex, they have the highest interpretability. And then the next is somewhere in between, which is machine learning. And then the deep learning ones are typically considered as a black box, right? Again, this field is evolving over time. Obviously, there are newer architectures even today that are more interpretable than compared to a simple neural network, but that's beyond the scope of this course. But typically, we consider them as black box, so they're lower interpretable compared to other family of models. Computationally, again, the easiest one is basically econometrics, and then the highest, the most complex one is deep learning, which is computationally expensive. It requires a ton of information. Remember, this is deep learning in general, right? So deep learning in general needs lots of information, and the processing, it's going to take time. And especially when we're talking about the sequential modeling, you'll see that why it takes a little longer compared to a basic model to train the model. Data suitability, of course, econometric works well when the underlying process is well understood. Again, think about this time series forecasting at a high level. Remember, what was the step one? Problem definition. What is the problem that you have in mind? What is the behavior of your time series? Is it well behaved? It is not well behaved. If you have a well behaved time series, and if you understand all the components, do not waste your time. You stick to a simple econometric model and it's going to outperform. But if the nature of time series is kind of vague and you don't have domain expertise and you just want to explore other forecasting tools to make sure that you're not ignoring, I don't know, nonlinear relationships, you can go ahead and use machine learning and deep learning as well. And for deep learning, especially if you want to incorporate some unstructured data set as well, like images, text, for signaling, for things like that, then you have to definitely use deep learning, because neither econometric or machine learning are able to handle those kind of data sets. So the core models that I'm going to cover in this course are simply, when it comes to econometric, we are going to cover ARIMA and ETS models. And for machine learning, I will do random forest, gradient-based, and boosting models. And for deep learning, I'm going to do RNN, LSTM, and I'll cover the CNN, right? And at the end of the course, I'll briefly talk about Facebook profit as well, simply because with all the caveats that it has, with all the limitation it has, it is still usable for some of the business time series. And it's I don't know, so many practitioners out there use it, even though today we know that they are not the best models out there. But I think if you know if you understand clearly the time series decomposition components, you can easily understand Facebook profit and you can appreciate its value. All right, that was pretty much it. That was part 3. In the next part, we are going to answer the question, can we beat Wall Street? And hopefully wrap up this module 1, which is the introduction to time series forecasting. Until the next one, take care. If you're looking to stay updated with the latest versions of the course's materials, please make sure to follow my GitHub and remember to refresh your repositories periodically. If you find yourself needing a bit more background in econometrics, machine learning, or deep learning, check out my other YouTube videos for additional insights. And for all the latest news and quick updates, don't forget to follow me on Twitter. Thanks for joining me, and let's keep learning together.